everyone, and welcome to another video lecture. Today, we are going to discuss applications of graph theory to some problems in communication systems. Once again, this is Mahid Mangontarum from the Mindanao State University main campus in Marawi City. A cellular network is a communication network where the link to and from end nodes is wireless. The network is distributed over land areas called cells, each served by at least one fixed location transceiver. These base stations provide the cell with the network coverage which can be used for transmission of voice, data, and other type of content. A cell typically uses a different set of frequencies from neighboring cells in order to avoid interference and provide guaranteed service quality within each cell. When joined together, these cells provide radio coverage over a wide geographic area. This enables numerous portable transceivers such as mobile phones, tablets, and laptops equipped with mobile broadband modems to communicate with each other. This is done with fixed transceivers and telephones anywhere in the network via base stations even if some of the transceivers are moving through more than one cell during transmission. According to a paper by Hall, in a cellular mobile communication system, the service area is divided into a number of small cells and each channel is simultaneously reused in some of the cells. The assumption here is that if a cell is adjacent to another, we can assign different channels to each cells. This assumption resembles map coloring where pair of adjacent countries are assigned different colors on the map. Here, the graph can be constructed as follows. Each node represents a country, and if two countries are adjacent, we set an edge between the corresponding two nodes. In an earlier paper, Sengoku and others noted that the channel assignment problem is equivalent to the node coloring problem. Apparently, the problem of finding an optimal channel assignment in cellular mobile communication systems can be modeled as a problem of coloring the nodes of a graph. From our previous discussions, this is an example of an NP-complete problem. Hence, we cannot expect the problem to be solved efficiently because of its NP-completeness. A more appropriate model is attributed to Tamura and others. This model takes into consideration the degree of Cochannel interference which usually creates an undesired effect in another channel. So if the number of edges between two nodes U sub 1 and V sub 1 is 1, and the number of edges between nodes U sub 2 and V sub 2 is k, the degree of interference between U sub 2 and V sub 2 is k times the degree of interference between U sub 1 and V sub 1. From here, we also define a generalized coloring problem by assigning colors to nodes in such a way that for each node V, the number of identically colored nodes adjacent to V is not larger than k. This figure shows an example of the said generalized node coloring for k equals 2. As we can see, the nodes colored with black are not adjacent. Also, the maximum number of white adjacent nodes is 2, which satisfies the given definition. It must be noted that the case when k equals 0 is simply equivalent to the classical node coloring. Let us now consider channel assignment problem in multi-hop wireless networks. One may see our previous video for an introduction to multi-hop wireless networks. For these types of networks, we assign channels to communication between two terminals. This is a kind of edge coloring problem. In this figure, channel A is assigned to the edge connecting X and Y and to the one connecting Z and U. Using the same assignment in a multi-hop wireless network, we may have the following figure. As we can see, terminal Y sends data in all directions when Y communicates with X. Since terminal U communicates with Z using channel A, Z cannot receive carrier from terminal U. In the classical edge coloring, we assign different colors to adjacent edges. The problem in this model when applied to communication systems is that co-channel interference may occur. Before proceeding, we will first introduce the notion of strong edge coloring. A strong edge coloring of a graph G is an assignment of colors to the edges of G such that every two edges of distance at most 2 receive different colors. The distance of two edges is at most 2 means that either the edges are adjacent or there is an edge between them. This figure shows an example of a graph with a strong edge coloring. According to Mahid in 2002, the problem of finding a strong edge coloring with a minimum number of colors is an NP-complete problem. In a paper in 2004, Tamura and others established a more appropriate model for channel assignment problem in multi-hop wireless networks. This model, which takes into consideration the co-channel interference, is stated as follows. If node V is adjacent to nodes U sub 1 and U sub 2, and the number of edges between V and U sub 1 is 1, while the number of edges between V and U sub 2 is k, then the degree of interference from U sub 2 in V is k times the degree of interference from U sub 1 in V. From here, we define a generalized edge coloring problem to be the assignment of colors to edges such that for each edge E, the CIR is not less than k. Let us consider the following figure. Here, a color is assigned to the edge connecting X and Y and to the edges connecting Z and U. Notice that terminal Z receives a carrier from terminal U at the same time while receiving interference from terminal Y. However, the number of edges between Z and U is 2 and the number of edges between Z and Y is 1. This means that the carrier to interference ratio is 2/1, which is equal to 2. The next application that we will consider is on mirror server location problems in networks. Server mirroring is a process through which an exact replica of a server is continuously created on runtime. It is a technique used for business continuity, disaster recovery, and backup. Duplicating the entire contents of a server on another remote or in-house server allows data to be restored if the primary server fails. Server mirroring is primarily implemented to create a fault-tolerant and redundant server computing infrastructure. This process works through specialized backup software that is installed on the backup server and the server to be mirrored. Besides backup and disaster recovery, server mirroring is also used in load balancing by providing identical data for fast downloading to remotely connected users. Apparently, location theory on networks is concerned with selecting the best location in a specified network for facilities. What we do is to assign mirror servers to nodes in the following condition known as the mirror servers condition. Under this condition, each node secures communication with servers even if some edges break down. The mirror server location problem in networks is the problem of assigning minimum number of servers to nodes. The figure below is a solution to the said location problem for k equals 3. Notice that there are three edge disjoint paths from node V to the mirror servers. A solution to the problem can be obtained using the following algorithm developed by Tamura and others in 1992. In this case, we can directly use this in graph theory. For further study about this algorithm, readers are directed to the paper of Arata et al. In 2002.